now I'll try to drive this crazy system. Slideshow. And let's see. I'll put the lighting down a little bit. And I think this is a clicker.
Let's see that.
That's for
forward, back.
Slides.
And
I
that.
think that's a.
Yeah. Okay.
Okay. Thanks, Bob.
Okay. Thanks. In this talk, I'd like to tell you the story of how part of Bell Labs, whose main goal was improving long-distance communications, made 3 major astronomical discoveries along the way. In the 1920s, Bell Labs got interested in radio research. Their headquarters was on West Street in New York City, which was electrically noisy, so they established several field stations in New Jersey to get away from the noise of the city. The initial interest was using high-frequency radio for transatlantic communication. They eventually concentrated all of their New Jersey efforts in Holmdel. In 1928, they hired 2 people of interest, Carl Jansky and Art Crawford. I'll be talking a bit about Carl Jansky. There are several other people. This is the crew in, I don't know, 1930 or something, in front of the building which they lovingly call the Turkey Shed. It was a long, thin building, but a lot of research was done there. Anyway, Art and Carl originally roomed together. Carl Jansky was tasked with understanding the sources of noise on transatlantic radio. He built this 95-foot long rotating antenna. Those are Model A wheels. The antenna was a Bruce design. Bruce was in that picture. It rotated every couple of minutes, I think. Worked at 20 megahertz. In addition to thunderstorms and man-made noise, he found a hiss, as he called it, which came from the same direction about the same time every day. He had a friend at Princeton who was an astronomer, and they eventually figured out that that this was coming from the galactic center. And it hit the New York Times. If you look over at this part of it, he says, there's no indication of any kind that this constitutes some kind of interstellar signaling or it's a result of some form of intelligence. So people were already thinking about that sort of thing. Well, this was the Depression. Bell Labs was on short hours. People were expected to do Bell system work, and there was very little follow-up for Jansky's discovery. Unfortunately, he reported the intensity of his result in volts per meter, and various astronomers had told me they didn't understand what that meant. If he had used the units we heard about a few days ago, like converting it to antenna temperature, astronomers might have been astounded and much more interested. Well, following that, the Holmdel group became interested in potential for microwave relay for distributing broadband signals. And here are some pictures I picked up of ideas that had happened. At one point, they were thinking of having a horn down on the ground and a reflector up at the top to aim it off in the direction they wanted to go. I don't know who drew this picture, but that's sort of the most absurd. The other approach was to take a widely flaring horn, put an artificial dielectric Fresnel lens in front of it and have something like that. But in 1946, Al Beck was thinking about this sort of thing and decided there must be some better shape than a flat reflector at the top. So he got out calculus of variations and solved for what the reflector ought to be. And he was chagrined to discover that he had reinvented the paraboloid. Thus was born the horn reflector, a relatively short horn with a parabolic section at the end, which turns the expanding wave into a plane wave. These were used for quite a few years in microwave relay on towers like this. You get a weak signal coming in here, goes down, is frequency converted, amplified, come back up and transmitted. The construction of the horn reflector means that there's very little coupling from one to the other. Both horns are shielded from the other side. In 1957, I went to Caltech for a PhD in physics. That October, Sputnik was launched. It seemed like an important thing to me. I didn't realize how important it was going to be to my life, but more about that later. My one cosmology course was taught by Sir Fred Hoyle, and philosophically I rather liked the steady state theory. In my thesis, I used one of the original 90-foot Owens Valley interferometer antennas to make a map of the Milky Way. We had built a switch. I took an ordinary 50 ohm load, stuck it in my thermos bottle, and poured liquid nitrogen in it, and compared the antenna to the sky, pointed the antenna to the west of the Milky Way, let the Earth rotation scan across. So the chart recorder, well, you'll see there are no computers in the control room. The chart recorder would do something like this. Later, you rip off the chart, put a meter stick across, and measure up above it. Fortunately for my thesis, the Milky Way is very thin compared to its diameter, but of course we're inside it. So in any direction we look, we're looking through some of the Milky Way. And so I knew it wasn't right, but it was good enough, and I got my PhD. At Bell Labs, let's see, I'm going to have to do something about this display. I'm missing some of my notes.
There's a problem. It's just showing one.
Yes.
You can figure that out.
Okay. I think so.
Okay. Take the time to correct it rather than be hobbled.
I wish I could.
How strange.
Oh. Okay. I guess I can do this. All right. Yes.
Yeah.
Okay. John Pierce was a polymath at Bell Labs. He had written the book on electron beam guns. He worked on communication theory with Barney Oliver and Claude Shannon. He supervised the transistor team and invented the name transistor. He started the first computer music group, and he wrote science fiction with a pseudonym J.J. Coupling. In 1955, he published a paper in Jet Propulsion titled Orbital Radio Relays. He was apparently unaware of Arthur Clarke's extraterrestrial relays in Wireless World in 1945. But anyway, he got very interested in communication satellites. So in 1957, when Sputnik was launched, he really woke up and got interested. In 1958, NASA proposed to put up the Echo balloon, and Bell Labs almost immediately proposed to use it as a test communication satellite. Okay. The Echo balloon was a 100-foot diameter metallized mylar balloon inflated in space. Think a very large party balloon. Now, if you send a plane wave up to this thing, it hits a sphere, the the energy scattered in all directions. So the return signal from such a thing would be weak. So Bell Labs decided to use two inventions. They had built traveling wave Ruby masers, the world's lowest noise amplifiers, in the Cold War work, and they decided if they put that on an ordinary parabolic antenna, pickup from the ground would override the noise of the maser. So they would build a large horn reflector antenna. Art Crawford was in charge of building this 20-foot antenna. The aperture is roughly 20 by 20 feet. The focal length is actually where the 20 feet comes from. So Echo was launched. They did this all in a big hurry. Echo was launched and used as a microwave relay in 1960. Eisenhower's voice was transmitted by GPL and received at Crawford Hill and sent out on the radio wires. I have to get my mouse in the right thing. Okay. Telstar was the first active communication satellite which was being built at the time. And the 20-foot horn reflector was fitted with a 4 gigahertz traveling wave maser, which was the downlink for the Telstar satellite. The idea was if one of the big Earth stations didn't come through, it could be used when the satellite went up. So after finishing my PhD and a one-year postdoc, I took a job at Bell Labs Crawford Hill. You can see the 20-foot horn reflector up here. They had cut the trees down all around so they could track satellites from horizon to horizon. Arno Penzias had been hired a year and a half before. He had finished a radio astronomy thesis at Columbia with Charlie Towns. So why did Bell Labs hire 2 radio astronomers? I'm sure what they told the upper management was, these guys will know about antennas, transmission through the atmosphere, a lot of things that we need for satellite communications. But I think there were 2 other things leading this on. One was a continuing worry that they had not properly supported Carl Jansky. They had not followed up on his discovery. Second, they were proud of having built this very low noise receiving system that had unique properties, and they wanted to see it used for science. So why did Arno and I go to this place with a small antenna? It's because of the unique properties of the 20-foot horn reflector. Those of you who know about antenna response diagrams will see that we have an isotropic level here, and the back lobes are more than 30 dB down below isotropic, which means if it's above the ground, we pick up the ground radiation more than 1,000 times smaller than the 300 degrees of the ground. So it's really negligible. The 20-foot horn is also small enough that we could get in the far field and make a proper gain measurement, and we could do some interesting experiments. So Arno and I got together and set up some things, a list of things we wanted to do. The important ones were measuring the absolute strength of Cas-A and a few other sources. Radio astronomers usually just measure ratios of strength. They don't really understand their antennas. But we could make a proper measurement and know how strong it was. That would also be useful for satellite communications because if you buy an Earth station, you could look at Cas-A, measure the signal-to-noise ratio, and you know the quality of the antenna and the receiver directly from that. Then we would shift to 21 centimeters, 1.4 gigahertz, and look for whether there's a halo around the galaxy that I might have missed in my thesis. Well, generally the question of what is the background was unknown at the time. It had been measured at about 500 megahertz and lower frequencies. And we would also do a better search for atomic hydrogen in galactic clusters than Arno had been able to do in his thesis at Columbia. So Arno had started making a helium-cooled reference source. This is C-band waveguide, 90% copper brass, going down into a tank of liquid helium with an absorber at the bottom, which radiates up at the at the temperature of the helium, 4.2 Kelvin. We had a series of thermometers along the waveguide so we could calculate how much was added by the loss in the waveguide. Also had a series of baffles here. It turns out you can get much more cooling, warming helium gas from 4 degrees to room temperature than you get by boiling it. So using the cold gas greatly improves the lifetime of the helium in your system. I, meanwhile, made a switch. Maybe I don't even need to explain it, but we had the antenna here and the cold load here. The two signals were put in cross polarization. This is equivalent to a half-wave plate which rotates the polarization. One of the polarization goes off to our receiver. And here's a picture of it in the system with an attenuator between the cold load and the switch point to add a little bit of extra noise if we needed it. And we could calculate how much came there. So a fellow named Dave Hogg and I rented a helicopter for a day, outfitted it with a transmitter, and here's a better picture of it. And let's see, right here on the side of the horn reflector is a laboratory calibrated reference horn. We knew the gain of that horn. We built two of them, or Ta-Shing Chu built two of them and measured in the laboratory, knew the gain. On the other side down here was a TV camera which was collimated with the beam of the 20-foot horn reflector. So the pilot's job was to go out a couple of miles and hover and stay in position. We would track it, and when it was in position, we would switch between the big horn and the little horn. And we had a 31 dB directional coupler, which made the two signals about the same. So we actually made, I think, one of the best gain measurements of an antenna this size that has ever been made, but nothing much ever came of it. So Arno and I built our separate parts, got it all together, and I guess on the 20th of May in 1964, we made this record, which as far as we can tell was the first time we had it all together. And it was a considerable disappointment. At this point, we have the antenna looking up at 90 degrees elevation. Power increases to this side. This is no added power to the cold load. The antenna is clearly hotter than the cold load. We could measure the atmospheric radiation, which was about 2.1, 2.2 Kelvin. We expected maybe 1 Kelvin from the walls of the horn reflector. So the horn reflector should have been colder than the cold load, but here it was clearly hotter than the cold load. By this time, we had made the measurement with a helicopter and didn't want to disturb things. So we spent about 9 months making sure that we had our receiver calibrated properly. We could do it several ways, get a reliable answer, and make a measurement of several sources in the sky. And during that time, every time we were not looking at some source, we measured essentially the same Uh-oh, what did I do? Oh, we measured the same excess antenna temperature. In fact, it's even better than that. We would start the day by pouring 25 liters of liquid helium in the coal load, and it would be filled up near the top. During the day, for the next 20 hours, it would boil off and the level would go down. So the waveguide would get hotter and hotter. But our temperature, our thermometry, and our calculations still showed the same antenna temperature. So we had considerable confidence that we were actually making a measurement. So after that period, we decided to clean up what we could and try to get to the bottom of this problem. So Arno and I got up in there, this is staged later obviously, in our lab coats. There'd been a pair of pigeons living in there. We would only work about once a week. So the thing was turned down. The pigeons could crawl up to the end of the horn. It was in the cab. It was cooled in the summer. It was heated in the winter. What a lovely place. Except these crazy guys came about once a week, turned it all around. They would fly off. As soon as we went away, they would come back. Anyway, there was this white dielectric material inside the horn reflector. And we thought that might have something to do with it. So we got up there and scraped it all off. And you can see that we put conducting aluminum tape with special conductive adhesive over the joints in the antenna, because that could have been another source of problem. None of this made any significant difference. So we had a whole series of sources of potential problems that we had pretty much ruled out. Well, probably don't have to go through all of that. Anyway, one fine spring day in 1965, Arno happened to call Bernie Burke. And neither of them remembers what the original point of the conversation was. But at the end, Bernie Burke said, "What's going on with your crazy experiment?" Now, the background to this is that sometime in the previous 6 or 8 months, they had been on an airplane together going to a meeting in Canada, and Bernie was pumping Arno on what the two of us were going to do at Bell Labs. I think there was an undercurrent of, why aren't you guys at a proper research university? But anyway, Arno told him the various things we were thinking of doing, and Bernie said, "There's no halo around the galaxy, you're wasting your time." So, so at this point, Bernie said, "What's going on with your crazy experiment?" Arno laid it on him. We had all this excess noise at 4 gigahertz. We were almost certain there should be nothing like that based on 500 megahertz measurements and the spectrum. So Bernie said, "Oh, you ought to call up Bob Dickey at Princeton." Now, Bob Dickey was an excellent physicist who, during the Second World War, worked on microwave receivers, wrote one of the Rad Lab books, which I remember looking at to learn about microwave receivers, and really got into microwaves. After the war, he got interested in gravity theory and invented the Brons-Dickey addition to general relativity, trying to find some way of proving that you needed the extra terms, which I think he never did. Anyway, he started thinking about cosmology and thought about a Big Bang and realized that in fact, he liked the idea of a repetitive Big Bang, oscillating universe. And he realized that after the first one, for sure, when all of that entropy comes back together, it's going to be hot. So it would be full of radiation, and when the universe expands again, the radiation would cool off. And having thought about radiation, he realized that it would be microwaves. So he was at Princeton. He got 2 very good postdocs. He got Jim Peebles. He asked to make a calculation of what we might expect, and Dave Wilkinson to make a receiver to look for it. Well, it takes longer to make a receiver than to make a calculation usually. And Jim finished first. He was asked to give a colloquium at Johns Hopkins, and he went to Dave and Bob and said, "Is it all right if I talk about my calculation?" They said, "Sure, we're so far ahead no one could catch up with us." So he went off to Johns Hopkins, gave a talk about radiation from the Big Bang, and a fellow named Ken Turner was in the audience, who was a good friend of Bernie Burke. He went back to the lab and told Bernie about the talk, and something like the next day, Arno called Bernie. So, so Bernie was aware of this possibility. So the next step is that I guess Arno called Bob, and Dave Wilkinson has told the story that they were having a sack lunch in Bob Dickey's office. The phone rang. He picks up the phone. They hear atmospheric radiation, sky noise, antenna temperature, all the things they were interested in. Their ears really pricked up. At the end of the conversation, Dickey put the phone down and said, "Boys, we've been scooped." I think Bell Labs had a good enough reputation that they figured if we said we'd done it, we probably had done it. Anyway, the next week they came over. We showed them what we had. I think they believed it right away. We went down to the conference room. They told us about Big Bang cosmology and the possibility of thermal radiation. So we wrote 2 separate papers. In those days, papers weren't so long. Ours was about 2 pages. I think both sides thought that their result might be true even if the other one wasn't. So we described the measurement, they described the theory. At that point, cosmology had hardly ever explained anything. So we thought there may be some other explanation for this. Well, on May 20th, 1965, a year after our first measurement, 2 things of significance happened, at least to me. One of them was Walter Sullivan, who was sort of the chief physics reporter at the New York Times, called up. We happened to be up in the antenna, and he asked a whole bunch of questions about what we had done. Apparently he had a mole at the Astrophysical Journal office, and he'd heard about this. And I think he'd seen both papers, probably. The other thing that happened, I grew up in Houston. My father came for a visit that evening. He had business in Hightstown, New Jersey, 15 miles away or something. We had his 2 grandchildren, so he spent the night with us. The next morning, I was still kind of behaving like a graduate student. He got up bright and early, got dressed. We were starting to make breakfast. He walked down to the pharmacy, about a quarter of a mile away, came back with a copy of the New York Times. And there was our antenna and the description of the cosmology and what we had measured. A wonderful time for both of us. Anyway, at that point, I think I started to believe maybe people are taking this cosmology seriously. And both Arno and I needed to catch up on cosmology some. We took a series of lectures that Dennis Sciama gave in New York. He was one of the early steady-state people. I think he was the professor of Stephen Hawking. Anyway, we learned a good bit of cosmology from him. So about a year later, Several people had made measurements, although at this point there was no indication that that it was necessarily black body. It still was along the Rayleigh-Jeans curve. The rocket, I guess we didn't see rocket measurements yet. There were rocket measurements later, which actually were up in here. Apparently they measured some of their exhaust or something. Anyway, it was quite a few years before the spectrum was really shown. Somehow I don't have a picture of the Kobe spectrum, but it is a remarkable black body that Kobe measured. They show a graph, and then they tell you that the error bars are entirely within the line that's showing the black body. And I don't have to tell you about early pictures of the universe. This all turned out to be very useful for cosmology. Going back a bit to 1932, George Southworth at Bell Labs demonstrated propagation of centimeter waves through, or actually they may have been longer, may have been tens of centimeters, through a waveguide. The idea of waveguides had been floated before. Even Lord Rayleigh talked about the possibility of a waveguide, but no one had actually done it. He actually filled his waveguide with distilled water to get, he only had the pipe this sort of size, so he filled it with distilled water to have a high dielectric constant in order to get his UHF, I guess, waves to fit within the waveguide. In 1933, a physicist and mathematician got together and calculated various modes of a circular waveguide. And they discovered this mode, the circular electric mode called TE01. The wonderful thing about this mode is that the electric field is that way, and so it stays away from the wall of the waveguide. And it's a very low loss mode, although it requires a much larger waveguide than the fundamental mode would have. So it's a very overmoded waveguide, but it can be very, very low loss. So Southworth moved to Homedale from AT&T. He and Russell Lowell started investigating millimeter wave detectors using a spark source, and waveguides were developed. Here's a picture of Southworth. The promise of wideband, low-loss transmission of millimeter waves through a waveguide really remained as a driving force at Homedale, and the interest increased as technology developed. When I joined Bell Labs at the newly completed Crawford Hill in 1963, a millimeter wave waveguide system was under intense development. It used 2-inch diameter waveguide and could propagate 38 to 120 gigahertz. And they figured they could make a transcontinental transmission system out of that with a repeater every 25, 30 miles, something like that. By 1975, a system was developed, and it was shown that coast-to-coast transmission was possible, but it wasn't yet needed. It turned out picture phone didn't really sell, and so they didn't need all the bandwidth they thought they did. By then, the Crawford Hill group, people had made low-loss optical fibers. The Crawford Hill group shifted to optical fibers, and you can think that all of this waveguide work was a loss, but I think their attitude toward optics as RF engineers caused them to do things differently than optical people would have done. So I don't think it was all loss. In 1966, as the excitement of discovering the CMB was calming down, Arno and I were reminded by our lab director that we were expected to work half-time for the Bell system and do radio astronomy half-time. So we both took on communication-related jobs. I put together this sun tracker, which used the sun as an artificial satellite and measured the attenuation on Earth's space path at 20 and 30 gigahertz, which were frequencies that Roy Tillotson was interested in. The heliostat wobbled on and off the sun, used a Dickey switch, and I could measure 30 dB attenuation. Turned out, I finished up in late November. December the 12th, there was a very heavy rainstorm. The sun disappeared in my system. More than 30 dB attenuation. While we were doing this, Arno was doing some observing at NRAO, became more aware of the 36-foot antenna at Kitt Peak, which had been designed for millimeter wave astronomy using Frank Lowe's bolometers. If you look at this antenna carefully, you see that the focal structure is extending way out. Turned out Frank Lowe didn't know how to match his bolometers to anything faster than f over d of about 0.8. So they put a very long focal length on this antenna. Anyway, by the time they got it going, Frank Lowe had moved off to other things. And we became aware that it was available for doing millimeter wave astronomy. Charlie Burris at Crawford Hill had learned how to make very good Schottky barrier diodes. Lithography at the time was kind of good for 10 microns, but using some tricks, he could make an array of 2 micron dots and with a mask, and he could clean the gallium arsenide under it and deposit metal on it, making a Schottky barrier diode at each of these points on the wafer. Merlin Sharpless, one of the people in the original picture, had used this scheme for making millimeter wave detectors. The mount here had a taper down to a very low impedance waveguide. This was the IF connection. The pin came through here. The semiconductor was there. Originally, it was just a piece of silicon, and a cat's whisker was on this. You sort of wiggled it around till you got something like a diode, and then used it as a diode. Well, so Charlie put his Schottky barrier diodes in there, and it worked very well. And he made an 80 to 90 gigahertz receiver for us, which we took to Kitt Peak and discovered that the 36-foot still wasn't quite ready for prime time. They didn't quite know where it pointed. If the sun shone on any piece of it, it would warp out of shape, and the drive system wasn't very... Anyway, whole series of problems. The one thing we did was to take one little track in the sky and repeatedly scan past it and add it all up, and showed that there was no extra fluctuation which could come from the microwave background being built up out of a series of point sources. But other than that, scientifically, it was sort of a loss. So we left the receiver at NRAO, and Charlie supplied them with diodes for several years. In 1970, the 36-foot had been understood much better and was ready for real observing. Arno invited Keith Jeffers, an atomic physicist, to join us to do millimeter wave spectroscopy. We decided if we moved to the next smaller waveguide size, there were several interesting molecules we could observe. Arno had been a student of Townes and Towns in 1955 had a list of likely molecules in interstellar space. And the obvious one was CO. At that time, the interstellar medium was thought to consist of synchrotron emission, all of the bright stuff that Jansky had seen and most galactic radio astronomers saw, ionized hydrogen regions, atomic hydrogen, dust, but no one was thinking about molecular regions, except maybe for Phil Solomon. Several molecules had been discovered besides the original, or several line sources, besides the original hydrogen source discovered here, but none of these actually pointed to extensive molecular clouds. So Charlie Burris made us a new mixer in RG8 waveguide rated for 90 to 140 gigahertz. Sandy Weinreb at NRAO offered to provide most of the auxiliary equipment, a filter bank, a frequency control for the klystron, and he sent a front-end box and a control lab to Bell Labs, control box to Bell Labs. Keith Jeffords and I spent 2 very busy weeks wiring our receiver into this thing and didn't quite finish. Someone at Bell Labs quipped that Arno had the 2 best technicians at Bell Labs working for him. So when the time came, we shipped it to Tucson. Sandy, Keith, and I went to the 36-foot to get it going. Each of these parts had its own way of failing. The diodes would sometimes just stop making contact. The klystrons were really iffy. You paid $5,000, the price of a Cadillac, with a 500-hour guarantee. And sometimes they would just spark, which would blow out the transistors on Sandy's phase lock loop. There was a pair amp with unstable gain. Sometimes it would oscillate. It would pick up the Phoenix radar, aircraft control radar. We had a beam switch, which was done by moving the feed horn and bending the waveguide. Occasionally the waveguide would break. The antenna computer kept crashing. The brakes didn't always release. It was still sensitive to the sun. Anyway, after 3 unsuccessful days, working very hard, I'll assure you, Sandy had to go back for some meeting in Charlottesville. He later told me he was very discouraged. He didn't think this experiment was ever going to go. However, a little later that day, Keith and I got it all working at the same time. Remarkably, we took off the short cables and put it up at the focus of the antenna, and it continued to work. So I asked the operator to point to the Orion BNKL region, which was the most likely source on our list of candidate sources, which was up at that time. The filter bank was really a bank of analog filters, and each filter had an analog lock-in amplifier, and each of these systems had its own offset and gain. And then it was followed by integrators. The integrators had 2 modes. One, a simple integrate mode, and the other was a 2-second time constant. So when nothing else was happening, we'd switch it to the 2-second time constant. And there was a readout which would display the 40 channels across this oscilloscope. So after asking the operator to point to BNKL, I was looking at the oscilloscope. So there was this cluster of points flickering around on the oscilloscope, and at some point, some in the middle went up. I said, "Oh, did you get to the source?" He said, "Yes." I said, "Please move off," and they went back down. So after all this work to make the best receiver we could, we discovered CO in about a couple of seconds. Another story about that is when I gave this talk at Berkeley, Jack Welch said that they had tried to talk Bell Labs into giving them some of these diodes. And if they'd had the diodes, they would have beat us to it. If they had made a 1,000,000-degree receiver, they could have found CO. So our filter bank wasn't quite wide enough, and we were frequency switching to make a full spectrum, but I patched together later two sections and made this first spectrum of the BNKL region. And I'm still kicking myself for ignoring these wings on here. In 1957, Ben Zuckerman, one of our competitors, pointed out that this indicated bipolar outflow from that region. And a whole industry of bipolar outflows grew from that. So look carefully at the results you get.
What is it about the wings?
A simple Gaussian would have cut off about here. But the wings represented not just motions in the cloud, but a bipolar outflow from the central condensation. And lots of sources have these things. It's entirely different physics.
But nobody else saw it either for about
No one's,
2 years.
yes, I don't know. I'm not sure why. Of course, as soon as you point somewhere else, a little off the center, you don't see the bipolar outflow. It's only right at the center. But somehow, we were so busy finding new molecules that we ignored that. So remarkably, our first observation was the brightest CO source in the sky. After exploring it until it set, we went to sleep. We were missing sleep at that point, and slept until the next morning in a period which we, for many years, called dead time, because the galaxy was down. There were no interesting molecular sources. We got up the next morning and found CO in several galactic H2 regions. So millimeter waves allowed rotational transitions of many species to be observed. It was really an amazing time. Well, first of all, let me go ahead. We had many joint projects with Pat Thaddeus and Phil Solomon and their students. We worked very hard. There were a lot of new molecules and sources and a lot of instant gratification. Looking back, I remember a time or two when we were looking for something and 24 hours went by without finding it. And I really started feeling depressed. Given the way science usually works, that seems pretty strange. Later, we got involved with the millimeter MWO with the University of Texas, and we built the 7-meter antenna at Crawford Hill. This was another sort of combination of radio astronomy and communications. The communications people wondered how close together in orbit can you put two satellites and actually so the signals will not disturb one another. Will a rainstorm scatter from one to the other? So this offset antenna was built with a wide field of view. A little bit off the center, we had a couple of receivers for the satellite. On center for the millimeter waves, we had our receiver for millimeter waves. When the weather was good, we did astronomy. When the weather was bad, we looked at the potential satellite communication. So it was an easy decision what to do. And once we had a solid state LO instead of these expensive klystrons that kept failing, I set it up so that the thing could observe by itself for at least half a day and often for a whole day. You could just set up a list of things you wanted it to do and it would go do it. So we mapped many things in that mode of setting it up and let it do things. Here's Orion A and B cloud that we mapped. In 1994, as Bell Labs was beginning to change and there was much more emphasis on doing things for communications and some other problems I don't want to go into, I retired from Bell Labs and came here to work at the CFA with the SMA, one of the outgrowths of millimeter astronomy. And it's been a lot of fun doing that since then. And of course, ALMA has been built. Millimeter wave astronomy has really taken off. I guess not long after we got going, the NRA proposed building a 25-meter telescope. About 1980, NSF declared that they were not going to fund that telescope. Think of something better. I arranged a couple of meetings at Bell Labs inviting the millimeter astronomers to come and think about what we wanted to propose. And after that, NSF had the Barrett Committee to do the same thing. Result of all of that was a proposal for a millimeter wave array, which eventually combined with European efforts led to the construction of ALMA. Well, let me finish by saying that those guys in 1965 had no concept of how important the CMB was going to be. You may have gathered that there was no real aha moment, other than maybe looking at the New York Times, in the discovery. We were searching for the problem for a long time, and then we didn't really believe in the cosmology. Anyway, the importance of the CMB only we became aware of the importance over the years as theorists developed theories of what the Big Bang would do, and technology got better so better observations could be made. It is, however, very satisfying to look back and see that we did our job right and to see how much has come from the CMB. The discovery of CO, on the other hand, brought almost instant gratification. Betsy remembers that I called home shortly after discovering CO. I'm normally kind of a quiet person. She says it's the most excited she ever heard me. So I feel very lucky that I had a job at Bell Labs with generous support. There were many experts on many fields at Bell Labs. We've heard of some of them. A lot of the things we do in radio astronomy were started at Bell Labs, or a lot of the things we understand. When I entered the workforce, the nation, perhaps shocked by Sputnik and remembering the contributions of scientists to World War II, understood the value of science for its future and was willing to spend some money on being a world leader in science and technology. In any case, it's been a wonderful ride. Thank you.
Bob, you will take a question or two?
Yes.
Maybe.
I've just about used up the whole hour. But
Yeah, you were actually right on time, but then the introduction was 5 minutes or so. So, I don't know, let's start with David.
Hi, I work on that telescope now.
the
The 12 meter.
12 meter?
It used to be the 36 foot,
Yes.
so
What is it doing now?
It's doing the same thing.
Oh,
When we get a new thing built, we point it at Orion and look for CO. And it takes us about, it's instantaneous, and the line
Right.
is like, "Rrrr."
right,
But yeah, so it still does the same thing.
right.
It's just doing better at it. But
Good.
I gave a talk earlier today and showed a picture of the next generation of filter bank after that, which we're finally turning off after 45 years.
That was.
The folklore is that the pigeon poop made a difference, but you seem to say
No.
that you scraped it off and it didn't change.
It didn't change much. It made a little difference, but not very much.
Not a CMB worth.
No.
And did you
Not
publish
as-
the results in the Journal of Ornithology?
No.
Well, you didn't mention the capturing the pigeons.
Oh, the fate of the pigeons?
Well, that you sent them in internal mail or something.
Yes. Well, we bought a have-a-heart trap, and we put it where the receiver normally is, and the pigeons came up and got in it. So we caught the pigeons. We put them in a big cardboard box and went to the company mail, addressed it as far away as you could go in the company mail, which was Whippany, New Jersey. And Arno happened to know a pigeon fancier there, so he addressed it to the pigeon fancier. And pigeon fancier got this thing, opened it up. These are junk pigeons, and let them go. Well, Whippany is about 24 miles as the pigeon flies from Crawford Hill. So they were back before long. And in the name of science, our technician brought in his shotgun.
Any other questions? Ron?
Yeah, so you said you were working one day a week. What did you do the other 6 days?
Oh, we were preparing things. We had to make a lot of hardware. Decide, when we put 25 liters of helium in the maser and 25 liters in the coal load, it would last for 15, 20 hours, and we didn't want to do that every day. But there was always, a lot of that time we were trying out one thing or another, and so we would actually operate not on a schedule, but when we had something to try. Yes, Nimesh.
I read something about Bob Beakley having a measurement of CP with a small horn from MIT when he was working on
In 1946,
something like that.
he published a paper in which he measured, his paper said that the background he couldn't account for was less than 20 Kelvin.
Right. I think, was it observing, he was observing the moon or something?
I'm not sure what the other observations were, but he had done a sky dip and subtracted all of the sources of noise that he knew about, but his accuracy was only that he could say it was less than 20 Kelvin. By the time all this was happening, he'd forgotten about that. Someone had to remind him that he'd made a measurement. I think he had also forgotten about, I didn't go into Gamoff's and Alpha and Herman's predictions. They had gone through this whole idea of understanding the Big Bang. They had their nuclear physics wrong most of the time because they wanted to make all of the elements in the Big Bang. But anyway, they actually calculated at one point, I think Alpha and Herman published a paper saying that it ought to be about 5 Kelvin, which is remarkably good considering the numbers they had to work with. Maybe they were just lucky. But they had predicted it, and in fact, they even went to some radio astronomers and said, "Could you measure it?" And they were told, "No, that's too small. There's no way to make that measurement." I think Arno has suggested that radio astronomers had things they thought were more important to look for. But I'm convinced, well, first of all, Dave Wilkinson's first receiver, it did have some transistors in it, but it basically was something that could have been built at the end of the Second World War if someone had wanted to do so. The helium might have been kind of expensive, but if they'd really been experimentally oriented, I think they could have gone out and made a measurement.
I should take one more question. Is there one more question? Guess not. Okay, well let's thank Bob again. Really great. Amazing history. 24 hours, huh? And you were patient.
How do you actually get?
I invited him.
To go around the curve.
Are you giving us a ride home?
Actually, I might.